So while she gets set up, I would like to introduce the speaker for this week. So we are very pleased to have Dr. Caro here. She's an assistant professor here and in the high school, and she is an active member in the youth experience club here. And most of her work is related to building and designing interfaces for teaching math to youth and for adults. So so I think that is something what she's going to talk today. So I will let her take the stage.
Hi everyone. Thank you for the introduction. We've been having some technical difficulties because I insist on building my presentations in Keynote on Apple, which is way better than PowerPoint. But then of course the string of dongles that we had didn't work. So I'm going to be presenting using a PDF, and there's going to be some interesting shifting to get to the video and so on. But it should be fun. Okay, I don't want to comment on this. Thank you. Anyone know how I make this gigantic?
Probably download it and open it.
Technology. Thank you. All right, well, I'll start. I'm Caro Williams-Pierce, and today I'm going to talk about designing for mathematical play, feedback, and failure. And I hate PCs. Where did it go?
I'm Caro and I hate PCs.
Yeah. Okay, is that good enough? Good enough. Yeah.
That's awesome.
This is currently in press in a special issue of the Journal of Information and Learning Sciences on designing for play in particular. I want to apologize for not being here more often the last couple of weeks. I was I was in Turkey, and it was fabulous.
Press F11.
F11, seriously?
Yeah.
Where is it? Ah, it's beautiful. Thank you.
I got you.
Okay. So I was here. It looks even more gorgeous on my screen. I had an amazing, wonderful time, and that is my reason for not coming more. So I'm super excited to be here, presenting to you all. I'm super excited to see you all for the rest of the semester and actually be able to come to more of these talks. I'd also love to talk about Turkish food. If anyone has any good recipes that I can duplicate here with American ingredients, let me know. So, we're back to here. Also, I'm one of those speakers that uses notes, but not today. Okay. One thing to keep in mind is what I'm going to present on today is not an empirical piece. It is a theoretical, designed piece based upon previous work that I've done. Yes. Okay. So I'm going to start by talking about my motivation. I'm going to give you an introduction to 3 different microworlds: GeoGebra, Rolly's Adventure, and Lynette. GeoGebra is a mathematical simulation in which you can create objects like triangles and then you can manipulate them. Rolly's Adventure is a video game about learning fractions, multiplying fractions that I built. And Lynette is a cognitive tutor. I call it a cognitive tutor, although I believe it's called ITS now. But the Lynette is built upon this long history of cognitive tutors out of Carnegie Mellon. And this one actually includes some form of artificial intelligence to be able to simulate what the student is learning and to change their interactions based upon that. I'm going to then talk about provocative objects and mathematical play. Provocative objects is my term, mathematical play is what I do. Interaction analysis of these 3 microworlds so you can get a sense of which aspects of those microworlds contribute to mathematical play, and then I'll do a discussion and a conclusion. I welcome questions during this talk in a large part. Yes, hi.
Can you tell us what constitutes a microworld?
Ish. So it's a term that was created 30 years ago, and it's essentially just a digital world. That's a super broad term now. I use it because it's this nice way of capturing these 3 very, very different digital experiences. And it's so old that I have to cite it and justify it even when I'm publishing directly towards the community that 30 years ago created that term. So it's a little old, but I like it. So follow that model, ask me questions. So first, motivation. So now I'm a little, these are supposed to animate in, well, we're gonna see, I may end up with lots of duplicate slides that didn't work properly, and I'll just skim through them. So designing for mathematical play or mathematical learning is about crossing this walking this very fine line. Fulton et al. Did some work on mathematical play, and they said that mathematical play involves pushing the limits of the situation and following thoughts and ideas wherever they may lead. Hence, there are no obvious short-term goals for mathematical play. It is designed to allow complete freedom on the part of the solver to wander over the mathematical landscape. However, how do you design situations like that but still have learning objectives or learning goals or even an idea of what you want the learner to experience and learn? And Rousseau talks about this a little bit, by saying, like, teaching is the teacher with a true paradoxical injunction. Everything that she undertakes in order to make the student produce the behaviors that she expects tends to deprive the student of the necessary conditions for the understanding and the learning of the target notion. If the teacher says what it is that she wants, she can no longer obtain it. So this is a very careful balance. If I tell you what I want you to learn, then you learn the behavior to mimic your understanding. So how do we have a goal, like multiplying fractions? How do we design a digital space that allows some type of freedom, while at the same time doesn't tell them anything, but at the end of the day I can still say, perhaps they learned something about multiplying fractions. This is the sort of quandary that I work within. So, welcome to GeoGebra's front page. There are millions of people around the world who use this. That's one of the reasons I chose it. It's free, it's open source. You can build your own applets and upload them. People use them. There's thousands, probably hundreds of thousands, maybe even millions of apps on here. Can people see the slide okay? Okay. So you can get some hint of the different types of mathematics, like cross-sections of a cylinder, multiplication of natural numbers. But you can also see that almost all of them, the cross-sections of a cylinder one totally does. I think that screenshot just doesn't show it, but these all involve visual representations of mathematics. And it's in fact a simulation. So you cannot go into GeoGebra and create an impossible triangle. You can, however, create an impossible triangle on paper. And we'll talk about that a little bit more later. So simulations are a way of only truthfully interacting with the mathematical landscape that Fulton et al. Mentioned. This is Rolly's Adventure. This is the game that I built. I built it on Little Big Planet 2 using that platform on PlayStation 3. And my goal when I built this was to walk this very, very fine line between what game scholars say is the best way to design for learning, for games broadly, not just learning games, or serious games, and how people best learn fractions. And I merged those two and designed specifically to try to go right down the middle. And I flatter myself that I succeeded, so you all can decide. And then this is Lynette. So you can see looking at this looks far more like mathy. If you've ever taken a math class, this will look familiar to you. So there's an equation. It's all about balancing equations and simplifying down and describing what you did to get to that state. So yeah. This was going to be beautiful with the square animating in as I said things, and this was going to animate in, but we do what we do. Okay, so provocative objects have 5 characteristics that I've identified. Consistent and useful feedback, and high enough levels of difficulty and ambiguity that players experience frequent failure that is closely paired with that feedback. These are the 2 I'm going to focus on today. These other 3 I think are very important, but one of my major goals in the learning world is to make failure not a bad word anymore, and consequently feedback and failure is one of my primary goals whenever I do work and whenever I give talks like this. And then this is my definition of mathematical play, which some of you probably can't see. Voluntary engagement in cycles of mathematical hypotheses with occurrences of failure. And I'm going to break this down for you a little bit. So voluntary engagement, my push from voluntary engagement comes from the games scholarship field. So Jay McGonigal is a game designer, and she says that to participate wholeheartedly in something means to be self-motivated and self-directed, intensely interested and genuinely enthusiastic. If we're forced to do something, or if we do it half-heartedly, we're not really participating. If we don't care how it all turns out, we're not really participating. If we're passively waiting it out, we're not really participating. This speaks to me It does not speak to, I'm afraid, it does not speak to many students who are in mathematics classrooms. And this is what I want to get learners in informal or formal environments to be thinking. I want them to be really participating in mathematics. However, it's unfair to examine voluntary engagement and think about voluntary engagement with products like GeoGebra and Lynette, because those were designed specifically to support formal math learning. So I'm going to apply this with a much lighter hand in this talk than I do in most of my work. Cycles of mathematical hypotheses. This comes directly from the radical constructivist perspective in mathematics education. I primarily follow Amy Ellis's work on generalizing. She's one of the foremost math educator generalizing learning science people. So from her perspective, generalizing is an activity in which people in specific socio-mathematical contexts engage in at least one of three actions: identifying commonality across cases, extending one's reasoning beyond the range in which it originated, or deriving broader results from particular cases. She specifically talks about generalizing as involving iterative action reflection cycles, and these engage, you engage in generalizing activities, you begin developing generalizations as a result of those activities, then you return to your generalizing activities in order to keep developing and nuancing the generalization. So you're going through this action reflection cycle to produce generalizations. And those generalizations may in fact be wrong. After you test them through an action, you come back, you engage in generalizing activities to test the new generalization that you're working on, and you come back out. So this can go on forever.
And this is why you're so fond of failure.
Well, so this is one of the fascinating things. Failure's never mentioned in this entire body of literature.
That's what you're doing then. You're testing the thing until it fails over and over again to see its boundaries.
This is, I conceptualize learning as generalization, which involves failure and feedback. But if you use the word failure in a classic math education context, like I did this once when I was a grad student and I was in my theories of learning mathematics course or whatever. And I was like, oh yeah, and then she totally failed. And everybody just, they all gasped in unison. And I was like, oh, definitely, yeah. And I'll talk a little bit later about why failure has this completely different context in math learning, but also in formal learning more broadly. But yeah, I look at this and I'm like, oh yeah, failure and feedback. Oh yeah, video games. This is what I do when I play video games. So why is this such a big problem? And so, yeah, the next 30 years, I hope to radically change the math education community. Wish me luck. One of the very tricky things about this, though, is that this entire perspective is actor-oriented. So Joanne Lobato proposed a new version, a new way of looking at transfer that's actor-oriented. So if generalizing is learning, but what participants generalize is based upon what they see, then we can actually very rarely predict what they will generalize from a specific environment. We need considerable information about a multitude of things. We cannot build a product and say, I guarantee that any kid that goes through this is going to learn how to multiply fractions. This perspective is predicated fully upon that. How many people here are kind of horrified at the idea that you can't design a product and then say people have learned X whenever they played it? No one's horrified. Everyone's horrified? No one's horrified.
You're in an HCI.
This is good, and this is why I shouldn't have been in Turkey and I shouldn't have come to the other talks. Okay, next time you hang out with a math educator, you say something like this to them. If they're not a radical constructivist, they'll be like, but then what's the point of building any product? And as we talk, people talk about scaling up. People talk about building these magical things that will then send out to all these classrooms, and every one of those kids will suddenly do better on their post-test or do better on a standardized test. This pushes against that. Okay, so maybe this is why I should have been in high school my entire career. Instead of scaling up. Yeah, David?
Can I push back a little bit?
Please.
Being in the college of ed.
Yeah.
So taking the, well, in some level, I'm totally on board, and I think this is kind of, in some ways, the more realistic way to make sense of what's happening. But at the same time, if we have this larger agenda to educate a population in what we decide is oh, it's really important that everyone fundamentally understands and is able to do multiplication.
Mm-hmm.
We're to take this position that we don't, maybe they will learn, we don't know, it's impossible like by definition impossible to like design something that will get kids to learn multiplication. Like what do we do with that given like this larger
Yeah.
educational enterprise that we're
So, okay, so one thing is that it's not that we can't, that no one will learn. It's that what people will learn will differ, and we cannot, with the knowledge we currently have, predict that. So I'm not saying like if we design this space and have people play it, they won't learn anything, or that it's impossible that they will learn something about multiplying fractions. But they may very well, some of the kids may go through and, well actually in Rolly's Adventure, a lot of kids took a proportional view instead of a multiplying fractions view. And that doesn't mean that afterwards those things couldn't be built together in discussions in classrooms or etc. And because they're not wrong. You can absolutely perceive Rolly's Adventure through a proportional view rather than a fractional view. And that doesn't mean that there isn't some way to unify that understanding. But I think my point with this is actually more of a pro-teacher than anti-technology. Is that I believe it to be impossible to create a trajectory that does not require any customization, human intervention, or teaching in order to get a sense of where they actually are in their understanding. Yeah, so I mean, how about if I come back next semester and we just argue this all out? Because honestly, we don't know. Like, okay, so we are in a situation in which we have to move forward with teaching and supporting students in learning mathematics. We're also in a situation in which technology lets us do things like simulate mathematics in a way that hasn't been around very long. So we're in this unique position where we have to bring this huge behemoth education system with us as we move forward, but we have to move forward. And yeah, so I don't know the answer to that. But yeah.
So related to the design aspect, how do you then account for the fact that the teacher is also going to have to understand the range, so that they can see the range as well, and that they don't just see it as being, oh, this is just fractions, this has nothing to do with proportions or whatever.
That's a similarly gigantic question. And actually, I propose that we table that one, so don't let us forget it, but remember that one, because what is the point of designing for formal mathematical learning if we have no way of supporting teachers in understanding the actor-oriented perspective, in implementing technology, in bridging from that technology to the standardized tests, which are not going away anytime soon, so we might as well just settle for that, etc. I mean, that's just a gigantic question. So yeah, let's hold professional development and elements of the socio-mathematical context off towards the end. One of the things that I did not do in this analysis is I did not account for the context at all. And that was like, my goal was to focus specifically on this feedback and failure and how those may support things. But without actually accounting for, is it happening in a classroom or a library at home? Are there adults nearby? Is it an adult playing it? Without that information, like, man, we really can't say anything about learning or teaching with it.
I have a smaller question.
So maybe I can actually answer it properly.
So I think it's sort of a clarification question, right? So there's two versions of the claim that you made. One
Probably
is the
maybe
super
four.
strong version, which is we cannot predict what any arbitrary child or learner will perceive and therefore generalize.
Right.
A weaker, but not necessarily worse version is that we need a lot more information, but if we had that information, there
Maybe
is a orderly set of pathways that we can then predict.
Yeah. Okay.
And I'm trying to sort out which of these,
I align with it?
yeah.
Yeah. I mean, so I will say radical constructivism states that, like, essentially, we learn through our experiences, and our experiences are filtered by us. So, let's see, Dora Abrahamson said the other day, you see what you look at, and you look at what you see. And that's exactly it. Like, we as people are filtering our experience. As we filter our experience, we also, like, we're filtering our mathematical experience. that filtering means that it's based upon our previous experience, and it contributes to our future experience. So, okay. So the strong version being like, there's no way we can know, I will say like that's specifically like right now. It also, like, in a lot of the time, I go for the super radical side, because I think we make too many assumptions about how K-12 kids are like all the same. And that bothers the crap out of me. It's tidy, it's handy, it's more efficient to make that assumption. But what that does is leaves behind tons and tons of kids who don't fit this like narrow view of what a kid or a learner is. So my radical view is a push against that. The weaker view, so I think like I implement the weaker view more because the radical view can also be easily misinterpreted as being like we cannot ever predict. It's not that we cannot ever predict. It's that you have to sit down with a child and get a sense. And if you sit down with a lot of children and get a sense of how they learn, how they generalize, the mechanisms of learning, the mechanisms of generalization, the mechanisms of interaction, all of these pieces, then you can start to see these patterns. Those patterns do not guarantee that a single individual will follow any of those paths. It just gives you more of a sense of which paths they're more likely to follow. There are theoretical learning objectives or learning trajectories in math education that are part of this, which is like, so if kids are learning quadratic functions, here tends to be the path that they go on when we're using these types of tasks. But that's it. We cannot say that a kid that starts with his first task isn't going to end up over here. So like that's a weaker view, but it's still pretty bloody radical. Okay. Did I talk? Yeah, okay. So this is one of the reasons why everybody in my Theories of Math Learning class gasped. Failure in mathematics classrooms can be seen as arbitrary. And I cite Erlinger here. It's an old article from 1973, but I recommend you all read it if you can. It is amazing. It traces this one kid who comes up with his own idea of the classroom and math, and it's completely wrong, and he talks about how arbitrary math is, like, oh, well, it must have been because of something I didn't know, like maybe on Tuesday, 2 + 2 = 5, but I didn't really, whatever. Like, it's just incredible. So this is Benny's conception of mathematics. It's about, yeah. So anyway, it's fun, it's amazing. So failure can be seen as arbitrary, and it can also be seen as an indicator of ultimate failure. Like if you do badly on this test, that means you cannot do mathematics. And this means that failure is a horrific and unreliable experience for many kids when they're learning mathematics. Many adults too, I'd say. Whereas failure in games is absolutely normal. This goes back to the generalization cycle that Eric pointed out. Like, you fail, you learn by attending to the feedback that's paired with that failure, then you go back and try again. There is nothing permanent about it, and in most games, I hesitate to talk about games as a single object, but in most games it's not arbitrary. And in most games you trust that it's not arbitrary. You know that if you're not sure what happened, you know though that there's a piece of feedback that you need to learn to attend to that will tell you how to do it better next time. Alright, so failure is super important. This is also my favorite part. Alrighty, so let's get into this. GeoGebra. The applet I chose to examine is the Pythagorean theorem, which states, with a right triangle, the square of the hypotenuse is equivalent to the sum of the squares of the other sides. A squared plus b squared equals c squared. So what does this mean? So, yeah, a triangle, okay. This is a 90-degree angle here at the bottom, so this is what makes it a right triangle. This is the hypotenuse. One of the super interesting things about hypotenuses, I don't know, is that the right angle right there is always opposite the longest side. This becomes super important because if you square the hypotenuse, you can visualize it as literally squaring. Now, if you square this side, you're going to get a smaller square. If you square this side, you're going to get a smaller square. This side is the big square. So the hypotenuse is always the large square, which means that you end up with a small square plus a small square equals a large square. Okay, so that's the only reason that the Pythagorean theorem works. Oh, right, now we're going to do this thing. Come on, technology. Yes. Okay, John Golden wrote this, and I chose, so this is the applet that I analyzed. that I analyzed. John Golden wrote it, and he has a ton of applets, well, as you can see on the side. Some of them have typos in them, but whatever, the applets are great. And John Golden's also written for mathematics teachers about GeoGebra and how to use the applets. So,
You've hit the time limit of the.
Is that?
No,
And
there's
I'm
an
talking.
arbitrary time limit for the system
No way!
that you must override before. Yeah, we discovered this.
Tech
with-
help!
Does anyone, can
Tech help!
I don't believe there is a solution.
Is there feedback?
No, you have to
Other
like
than
wait.
just failure?
There's a cooldown period that we must initiate right now,
Okay.
but I don't know how to do it.
So here's the bonus. When I was in Turkey, I don't speak Turkish, and some of the folks I talked to didn't speak English. So we had to just use, help. Yeah, thank you. So we just had to use like gesture and grunts to explain things. I told an entire joke in mime, and the people I was miming to laughed at the right points in my joke. So I could probably do this using interpretive dance, but hopefully I won't have to.
Oh.
Okay, so GeoGebra. Okay, right. So John Golden built this this simulation to help students explore the Pythagorean theorem and other parts of the patterns that contribute to the Pythagorean theorem. It's based upon if you are really super into visualizations, then you should go check out. See, I want to say Erlanger. It's not. It's a book from 1873, and it's a visual representation of the first 6 of Euclid's theorems. And it is incredible. It is absolutely gorgeous. And the cover of this book looks an awful lot like John Golden's thing, because it all has to do with the fact that you take this triangle and you think about these squares that are built off of the different sides and how they have relationships to each other. Yay. Thank you. Is there something I can do so it doesn't happen again? Yeah, okay. Well. Okay, so this is what the kid gets. For those of you in the back, you might not be able to see, this is a light green square here. This is actually a very constrained GeoGebra applet. Often you can, let me hit the play button. Often with GeoGebra applets, you can click on these and stretch, and the square will stay square as it stretches in and out. John specifically designed this one so there's only 2 different interactive points. So this cycles it. And interestingly, one of the amazing things is that if you take a right triangle, like the one I showed you, and show it to a kid and say, is this a typical right triangle or a typical triangle? They'll say yes. And if you turn it at a weird angle, they'll say no. So this is actually a really important piece right here. And then this just moves around the screen. And the sliders are the part, yeah, okay. So the sliders control A, B, and C. Right there, okay. And you can see throughout this entire thing, as I'm sliding like this, so I'm adjusting the side lengths of the red square, you can see the other pieces move along with it. So the triangle that's in the middle stays a legitimate triangle. And to go back to what I said earlier, that might seem fairly simple, especially to you all who are incredibly tech advanced, but paper doesn't do this. Paper lets you just write the most ridiculous mathematical objects that don't exist. Okay, so let's see if I can remember how to get this to. Okay. So you're supposed to mess around with this and then see what patterns emerge. Do I have a 90-degree angle in there? Ooh, yes, okay. So this is where, so I now have a right triangle, which means that I now have spaces here. So these 2 triangles will add up to the volume of this triangle. Okay, cool. Now to get back to my thing. F11?
Yeah.
Okay. Oh. I'm really tech savvy, I swear. So, we talked about triangles, GeoGebra, you got a sense of GeoGebra. I'm just using the wrong document, right? Okay. So, with GeoGebra, interacting with the simulation is like interacting directly with the mathematics. The simulation acts as this proxy, and the feedback comes from the mathematics. So you cannot create an impossible triangle, like you can on paper and pencil. So the paired failure that comes with the feedback from the mathematics comes directly from the learner-driven goals, which can be big or small. The small ones are ones, as I was like messing around with that thing, if I were a learner engaging in it and just like trying to see some patterns, etc., I might have a tiny little goal. And I might think like, okay, if I drag this slider, then I think this square will get bigger. Just like a tiny little goal. And I might barely even be aware of that goal. And when I move the slider, if it doesn't do that, if it makes a different square change, I barely experience the failure of what I expected not happening. What I expected to happen, not happen. There we go. So I term these micro failures because they are ones that are not visible from the outside, because you all had no idea that I had that tiny goal, or really much of a goal at all for most of it. They are also barely recognizable to the learner themselves. So what does this mean for mathematical play? So one of the difficulties of microfailures is that they emphasize the action part of this iterative action-reflection cycle, de-emphasizes the reflection part. But without reflection, the learner is less likely to modify the mathematical hypothesis that's guiding their action, so this cycling process is less likely to occur. That's not necessarily problematic, depending upon your overall goals, but it's something to just keep in mind in these sorts of interactions. If you have a microfailure that the player barely notices, if at all, it's less likely that they're going to learn explicitly. So this is a mathematical landscape following Holton et al. It's visually represented, and it only allows these legitimate interactions. Again, so like triangle, if I drag one corner, the whole triangle's going to drag. So my conclusion is that GeoGebra is this sort of like intellectual playground. It supports but does not require mathematical play. There is feedback regularly. There is sometimes failure. And that sometimes failure means that even though there's constant visual feedback, these like cycles of mathematical hypotheses with occurrences of failure is less likely to happen. Okay, so we're going to move on to Rolly's Adventure. This is the game that I built. Super important to remember. This is what they get for the first screen, just without the big red boxes and letters. Which means they know nothing. They know exactly what you know right now looking at this, which is like, there's a thing up there, and like, I think I'm the rainbow person, and there's these dots and like random clumps in my way that have these weird symbols on them. That's what you know. So you have to engage in failure and feedback to figure out what's happening in the game. If you don't, then you're just stuck here forever. Okay, so the rainbow person is the avatar. This symbol actually looks like a hand in the game and means if you grab me, something happens. So this symbol makes the thing it's attached to become a button. Let's see. These are the labels for the buttons, although players often didn't notice them until actually after they've been playing the game a little while, because there's just too much new stuff all at once at the beginning. That's Rolly right there, who the game's named after. An evil wizard took them away from their family, and they had to rescue them. So, similar. Yeah, not a very strong narrative arc, I'm afraid. This is what I call the fraction block, so it's just a golden block that's in there. Again, the player doesn't know any of this language, and it's in a hole. And what the player finds out is that they need to fill the hole perfectly so that Rolly can get across to progress towards rescuing their family. So the very first puzzle, the golden block, is 1/2 of the hole. So what players usually did is they'd come in from the left because it's a side scroller. They would activate that first button, and a single gold block, like that block would disappear and another single gold block would appear. And then they'd experience failure, and I'll show you that in a second. If they grab the second button that has 2 dots down there, they'll end up with 2 golden blocks, and that makes a perfect ramp, and there you go with Rolly. All right, so. Okay, so welcome to failure. I love that example, and I particularly use it for math ed environments because I'm like, yes, I just set the student on fire, but look, he likes it. It's okay. Yeah. I really am just incompetent at disease. Okay. So, now I've shown you the failure. What I haven't shown you is the feedback. So this is a picture from a different puzzle in it, but hopefully most of you can see the entire level's on fire, except the golden block that is the feedback from their action. They grabbed a button, and it's what caused this quantity to fall in here. And then you can see Rolly, who has rescued part of their family already. So this is a tiny little bit of visual feedback. It's the only feedback they get. Yeah. So big playful failure. Small, nuanced feedback. So, but once players identify this goal of helping Rolly cross this gap, they begin attending to the feedback. They know that there is something that they're not attending to that is helping them achieve this goal state of helping Rolly. And the feedback is one of those, like, yeah, very few visual elements that is available. So I created 2 types of failure. There's fiery death, which you just saw, and these are my coding schemes. Fiery death, which sends them a little ways back in the game, and then they have to like spend the time that's really irritating running through. And then what I call permadeath, which actually sends them way, way further back. I changed these for presentations to School of Education people. Okay, but there are no micro failures in this. There's no opportunity for a child to fail and receive feedback without being aware of it. It's very, very clear. Failure is occurring. So what does this mean for mathematical play? So because there are no explicit direction, they have to engage in these cycles of mathematical hypotheses in order to move forward. Otherwise, they'll just be trapped in it. Note that I did not say that their mathematical hypotheses are correct. That's important. They have to engage in these cycles. They're engaging in mathematical play. Whether or not what they learn is correct, from my view, is less relevant. So each new puzzle is more complicated than the last, and this is a common way to generalize, and I'm sure that you all have conceptualizations of this. Like, why would you have a tutorial if, like, a tutorial helps people learn a little bit and move forward? And so it gets harder and harder and harder all the way towards the end. And then mathematical generalization works just like probably technology generalization, or whatever the common term is, where once you learn something, you can build on that and make it more complicated. Players actively experience and are penalized for failure, and the increasing difficulty of this arc and the frequent failure actually cause the players to develop this intellectual need to understand the mathematics, so they reflect, adapt, and learn as they go. However, given that this is my framework for mathematical play and my video game, we are not super surprised that it is awesome. That's a joke. It's not perfect, but it's pretty close. So Lynette. Yeah, no one can see that back there. Okay, this is the front page for Lynette, which is still under demonstration, under development, so it might have changed by now. This says -10. Oh, I can't see it if I stand there. JK. Okay, -10 minus 7x equals -1 minus 4x. I'm going as I start solving it, as I start solving it, you can see there's now green text in those empty boxes. That's me doing a step. It turns the text green specifically to say, yes, that is a mathematically correct activity. And then it asks me what I did. And this is a way of evaluating whether my understanding of what I did aligns with what I actually did. and it turns those green to say, yes, you did add 7x to both sides. And then you do this for the whole thing, so you keep going and it keeps tracing, so you can keep an eye on it. So what happens when you do something wrong? It turns the text red immediately, and you actually cannot progress at all until you have green text there. So what I did here, I think, is, oh yeah, I subtracted 3 from both sides, but I forgot to keep the positive 3 on the left to keep the equation balanced. So it just turns it red. This is actually a version of micro-failure because it's turning it red. Somebody like me is just gonna be like, oh crap, yeah, I totally forgot to keep that 3 there, like obviously. And so I'm just going to adjust it, it's gonna turn green, it's gonna let me progress. I'm barely gonna even notice that I failed because I'm like, oh yeah, absent-minded mistake. However, I can click the hint button. So when I do that, it says, write x plus 3 minus 3 on the left. It very much tells me exactly what to do. So, yeah. I guess not a hint so much, but this is interesting because Anderson back in like the 90s was working on one of the first cognitive tutors. This is at Carnegie Mellon. This is part of that long trajectory of history there. And one of the problems they had was that they had progressive hints. So like the first hint would tell you a little bit, and then you click it again and tell you more and more until eventually it would just tell you what to do. And so a number of learners, unfortunately, just clicked that button until they got the answer and keep moving forward. So they were like, this is a problem with designing hints. Well, one of the things that Lynette does, so like here, it's very explicit. My view of this is that it's written this explicitly for people who have forgotten more than I had forgotten. So I look at it and I'm like, oh crap, I forgot to leave the plus 3 there. Someone who's a little less familiar with balancing and simplifying equations is going to be like, oh yeah, that's right, I forgot, and then they'll type it out. Someone who really has, so it's a type of comfortable failure feedback that is actually fairly small. It's didactic, but it's useful for this population of people who know what the right answer is, but have sort of forgotten it. They don't know it super well yet. Now, if I do something super egregious, like I added the 5 and the plus 3 on that side, and it's like, no, that's not right. If I hit the hint button then, the hint is actually much bigger, so it's not as much do this thing to progress. It's like, okay, look, you have constants on both sides in the original equation. You have a 3 on the left and a 5 on the right. How can you have all the constants on both sides and no constants on the left? And that's like a bigger, broader question that actually brings them right back to the original equation. It doesn't try to push them forward from where they are, like with that horrifically incorrect option. It says like, go back to the beginning and reconsider what you're doing. So that's a stronger sort of failure. So my view with Lynette is that there's both formative and summative failure. Formative, how many people know the word formative and summative here? Okay. So it's something, yeah, good number, sweet. So formative, the learners can see their errors highlighted in red as they go, and they can also ask for assistance via hints. So the errors highlighted in red might also be a micro-failure. But this guides the learners actively as they're moving forward. The summative part is a weird summative part. So with like standardized tests, the summative part is like, oh, okay, you failed. That's it. That's all you get. Like, it is truly summative, and it dictates the next part of your life. In Lynette, Lynette bases the next problem upon what the learner does in this problem. So their future problem set is circumscribed by what they do in this current problem. Okay, does that make sense? They're going to failure and feedback. Yeah, and it's dictating the next step. So it's a weird sort of summative. It isn't saying, okay, that's it, you're dumb and can't do math anymore, or you have to retake this class, or whatever. What it's saying is like, okay, I see where you are, here's where you need to go next. And the learner is like never aware that this is even happening. Okay, so in Lynette, text-based hints pair failure and feedback. The learner admits that they're failing, and they ask for feedback every time they hit that hint button. And so failure and feedback, like on demand, so to speak, is actually a really interesting design choice. Although hints can be tricky, as we talked about. So what does this mean for mathematical play? Much like Rowley's Adventure, there's these increasingly difficult problems that push learners to generalize across these problems. However, performance is a proxy for understanding. This is not unusual. Yes?
Do you have any like problems where it just has the drop-down menus, or is it mostly defaulting the typing in the equations?
So in this version of Lynette, which is probably from like 6 months ago, so it's all, you type in the numbers and then the only drop downs have to do with which activities you're doing. So like, it says, let's see, right here. So like, yeah, type in, click the sort of action added from this whole drop down list, type in the component of that you acted upon with the adding, and then say where you added it. That's the only drop down. So yeah, it's absolutely possible that by now they've done something else. But my guess is that at the beginning, when they were designing this, they said like, it is far more valuable to have a sort of open-ended response space. Yeah.
Yeah, I was mostly wondering, as like sort of a link into that hint system, or instead of just like explicitly stating the hint, if there was like a way to uncover the hint through a, more micro-failure type way, like, if it knows that you're failing in a certain way, giving them sort of a constrained fail space.
Yeah. Well, so one of the interesting things about, so you've sort of foreshadowed something that'll come up in a little bit, which is that, well, okay, we're gonna wait on that. Yeah. Don't take it personally that I keep saying wait on your questions. It's a really good question. Okay. Performance is a proxy for understanding. Very common in math education. Generally by policymakers more so than actual teachers. So learners may be focused on generalizing how to perform, that is what to do, rather than generalizing their actual mathematical understanding across these problems. So from like Amy Ellis with her generalization work would be like, this is not mathematical generalizing because you're focusing solely on what they do, not what they think, like not what they experience, not what they see, not what they perceive, not what they extend. So Amy, and then consequently me, would say that means that we actually have no promise here that there are cycles of mathematical hypotheses. They may not be hypothesizing about much at all because they're just performing and we have no insight into their actual mathematical understanding. Don't tell Vincent Oliven I said that. Thank you. He's the Lynette guy. All right, so the formative failure actually prevents learners from experiencing the outcomes of their action. So if you think back to the last time that somebody said like, 2x equals 4, and you had to solve it, so you can, you can solve it, and then when you have the value of x, you can feed it back into the original equation to see if you're correct. This formative feedback actually prevents that type of feedback from the mathematics from occurring. I say that without judgment. I think, it might be worth it to have the formative feedback at the beginning and preventing the mathematics from giving that feedback later at the end. So my conclusion here is that mathematical play is possible, but not required. Okay, we're gonna jump into the discussion. And I really wish that I was slowly revealing the amazing points I'm gonna make, but instead they're right there. Okay, so we talked earlier about how failure is this like really bad word in math classrooms. So microfailures might actually be this perfectly sweet middle ground to include a way to include failure without evoking the negative context of failure in that environment. You may also be able to start with microfailures and then make them, so one of the problems with microfailures, right, is that the action side of the action reflection cycle is the part that's weighted. There may be less reflection by the learner. So if you could theoretically start with microfailures and actually have students generalize about the microfailures as they got bigger and bigger, such that what they generalized was failure is good. And then you can get to the point where they are aware that they are failing, they're comfortable with that term, they're comfortable with being caught on fire, etc. And then you can actually have failure that is much more overt, that will push reflection back up to be held equal with action in that learning cycle. Microworlds that represent mathematical objects and interactions differently from traditional forms will likely need bridging to that form. I have one of my students, Nihal, here today. Lead author on most of the pieces. One of the problems is, so Vincent Oliven actually did a study where he compared Lynette with DragonBox 12+, 5 minutes? Sweet, I'm right on time. Okay. And what he and his lab found was that playing Dragonbox didn't do anything to the pre and post tests. The pre and post tests were paper and pencil and used standardized representations of mathematics. The kids who played Lynette, on the other hand, had a really nice change. They did way better on the post test. And this is not surprising to Nihal or to I, because the mathematical representations in Dragonbox are so completely different that it makes no sense to assume that they can make any sort of connection from that context to the paper and pencil context. There needs some sort of bridging, and this might also come back into where teachers have a place in. Because, yeah, I love Dragonbox, but it's probably not gonna help you do better on your standardized test without some connection. So this is work that is ongoing. One of the questions that I have that I would love for someone to investigate is what about analog provocative objects? So card games, board games, any other sort of system. This is particularly important for schools and libraries that don't have a ton of money and can't have up-to-date technology and so on. So yeah, study board games, that's what I suggest. Okay, each microworld is different. One of the things that it is artificial for me to say there are games, simulations, and cognitive tutors, because in fact, those are not distinct populations. So, like Rolly's Adventure, for example, has an aspect of simulation in that if a player activates the 2 button, they're going to get the results of that quantity twice over without fail. So you cannot do like 1/2 times 3 equals 17. Rolly's Adventure will not model that sort of inappropriate mathematical behavior. So there's that aspect of simulation. Also, back to my radical perspective, it's important that we avoid theorizing about learning without actual evidence from learners, without knowing what they perceive, what their background is, how they generalize across these experiences. We have no idea what those learners are actually doing. Okay. I want to share this. This is next week. It comes with a free lunch. So, and it's on a Friday, so it does not conflict with this at all. Eric Knuth was one of my advisors at the University of Wisconsin. When I was there, he's one of the foremost algebra and student thinking experts in the world. Yeah, also he's the director of the STEM Center at UT Austin. That's where he is now. So, yeah, come and listen to him talk. One thing that's super cool is that he never blinks. It's like once every 2 minutes or something. So it's kind of, just be forewarned. It's not you, that he's not staring at you. He just doesn't blink. But he's also a delightful human being. Okay, so thanks to various folks. I think I'm good on time. So we have questions. Yeah?
So back to the action reflection space. Does anybody do a lot of work about when kids are working together, 2 kids cooperating on a game?
Mm-hmm.
What kind of experience?
Yeah,
Technology mediation.
That's also a huge field. Yeah, so I will say there's a huge emphasis in learning sciences on collaborative computer-supported collaborative, learning. Yeah. Okay. Now, so with Rolly's Adventure, there were when I was collecting data, some of the players were by themselves, like that little clip. Some of them brought siblings. One of the difficulties I have is judging whether or not those pairs accomplished more sophisticated mathematical reasoning because they were arguing with each other. Like, that's what I think. But the truth is it's also possible that these individual people were just as sophisticated in their reasoning, but I just had less evidence because they were less likely to say out loud. So that's tricky. I have a graduate student at UAlbany who is doing who's doing collaborative problem solving using the Portal 2 co-op mode. She's about to start collecting data with that. I don't know how many people have played that. Oh, it's amazing. Okay, I see him nodding back there and a big smile. Yeah, it's awesome. Okay, so she'll have something to say about that. There tends to be a lot of benefits. One of the big issues, however, with that sort of collaboration is that they're computers and systems are not always designed for actual collaboration. So there's this one bit of analysis I'm doing with Amber Simpson, Binghamton, and Cena, like John Cena, and I can't pronounce her last name.
John Cena?
Well, it's not John Cena, but it's
Wrestler?
yeah. I'd rather work with The Rock, I think, actually. Yeah. Okay. Sigene, pronounced Cena, like John Cena. That's the way I remember it. Anyway, okay, so she's awesome. She's somewhere in Indiana. We're looking at maker spaces, okay? We're doing this interaction analysis on this tiny little group data, and they're making a robot follow this path on the floor. They're trying to make a robot, okay? As soon as the iPad that controls the robot gets introduced into the group, it fractures. Suddenly there's like 5 kids grouped around the kid with the iPad. There's actually physical tussling, like not like punching, but like, oh, no, I want it, no, I want it. And they do this back up. And these are middle school kids, like, they should know that. But one of the weird things with this system is really one person can have it, 2 people can tap on it, sure, fine, but they have to be collaborative about it. They have to be talking about it, so they have to be friends. And they also have to be willing to bet that the person they're letting tap on it isn't going to try to grab it at one minute, right? So the use of a tool that is the only object that controls the robot, you can't see it unless you're close, you can't actually contribute to it unless you were the person with the possession of it, means that the collaborative aspect of that actually like fundamentally broke the group down, and they didn't get anywhere. So this long train of multiple references is to say there is evidence of very positive things happening with learning and generalizing and supporting reflection by talking to your partner in these spaces. There's also plenty of evidence that it actually will disrupt the design of the entire learning activity. Did I answer your question?
Really
Okay.
interesting, thank you.
Okay, sweet. Okay, wait, professional development, okay, David left, so we're good. But will you bring up your question again, the one we tabled?
Drop down.
What is the first, the second one?
Whichever one you remember, or one answered most.
What? One?
Drop down. Drop down?
I was more interested in the drop-down one actually, like where, like constraining the fail space, because I mean, if you can predict what the failure is going to be, and then because, you know, is there any relation between how constrained the fail space is and how micro the failure is?
Right. Yeah, I mean, I think that's a really interesting question, and I will say, like, the term microfailure is fairly new. It was actually independently coined by myself and Amber Simpson working in makerspaces. So I think it's going to become this, like, really big, interesting thing. But if you wander around saying microfailure, nobody's going to know what you're saying, probably. Okay.
I was sort of looking at like in terms of like the collaboration and how students communicate with each other visually, and it's really weird how they perceive the constraint.
Yeah. Okay. So one of my general, wow, there's a lot of things here. Okay, so first of all, my guess is that the drop-down option, when you constrain a space, you constrain, the types of interactions, the feedback, and the failure. You constrain all of that. You also constrain the possible learning. And so if there is someone who is actually just like messing around, it's better for them probably to have this sort of open space. So I'm imagining if we took Lynette and we said, here's a drop down, we're gonna do a drop down value. Like, what do you think the x plus 3 over here should look like in the next iteration? There are so many different ways you could go with that, right? So like, but let's say that there are 5 different options, and let's say 2 are correct, because it's absolutely like x minus 3 plus 3 is correct, so is x plus 0, so is x on the left side. So you have some of these correct options, and then you add some incorrect options. Suddenly you have this like actually weird literacy space where you have all of these different possible responses that a kid has to be able to read and understand to move forward.
And then it becomes problematic when they have to collaborate, because then they have to then be able to articulate
Yeah,
that to another person.
Yeah, I'm
Yeah.
still thinking about a single person just because with multiple people it
Yeah,
becomes
because
a
with a
whole.
single person,
Yeah.
they were enjoying the play, but the moment you threw into a collaborative environment, they started to like, sort of chafe at the openness of it.
Yeah, I mean, that's one of the, I think this is one of the reasons why collaboration is like such a hot topic, is because when you can have a beautifully designed space, but when you put other people in the mix, they will redesign that space. They will co-redesign that space in incredibly unpredictable ways. And so, yeah. Do people know Holland and their group's Figured Worlds book? It's a book essentially about how the world that we inhabit is fundamentally influenced by the cultural assumptions that we bring to that space. And those cultural assumptions dictate what is possible for us to do. So you could have the same table, but people from different backgrounds will experience what that table allows you to do in fundamentally different ways. So if I drink a lot, I might be like, ooh, sweet, dancing, right? But if I'm not, that was funny, come on. But if I am not an alcoholic, then I might be like, oh cool, I can put my laptop down on this, right? That table is not just a table, because I figured the world around me based on my past experiences. And I think like one of the drawbacks is you take two people from different figured worlds and you squish them together, and those figured worlds can conflict with each other fundamentally in unpredictable ways. You standing there mean I'm out of time? Yeah. Okay. I haven't even finished my pizza yet. Come on, people. Okay. I'm done. Thanks. I'll be here for a minute.